This is our third lecture on electromagnetic waves, and today we're going to be focusing on transverse electromagnetic waves, of which plane waves belong to this class. So last time we had a look at the wave equation, and we came up with a very particular solution to the wave equation for the electric field, and I'll just highlight this solution here. So here is our plane wave for an electric field that's polarized in the x direction that only has variation in the z direction. And you'll recall that this was a very specific set of assumptions that we imposed on the solution just for illustrative purposes. And later today we will see how to relax these restrictions. But here we see that the x component of the electric field as a function of space and time has this cosinusoidal dependence with this cos omega t minus kz type of dependence. And so this leads to a wave that we identified last time as traveling in the plus z direction. It can have a phase a constant phi plus attached to it, which only shifts the curve left and right, doesn't change the fundamental behavior of this wave. This wave is also uniform in that the electric field is uniform everywhere in a plane normal to the z direction, as we see in the sketch on the right hand side. Anywhere where we sample the electric field in a plane that's normal to the z direction, we get the same magnitude, which is E naught plus, and actually the same phase, which is the argument to the cosine. So this is a uniform plane wave, often abbreviated as just a plane wave, and this is traveling in the plus z direction. We had a look at a plot of this function where we can see we have clearly a sinusoid. The peak amplitude of that sinusoid is again the magnitude of E naught plus, which is in general a phasor or complex valued quantity. And that at successive instants of time, in increasing time, this wave moves to the right. And in order to remain at a constant phase position, so a constant, if we're at some amplitude position here, A, that requires that the argument to the cosine remain constant, and the only way that I can keep the argument to the cosine function constant if time is increasing is for kz, or more specifically z, to be constant. So, and this is how we were able to justify that this particular solution to our wave equation travels in the plus z direction. Now we can actually evaluate a couple of things related to this wave. We can actually work out the velocity that these 3 points are moving at. We've established that they're moving to the right in the plus z direction, and you might guess that they're related to the wave velocity u that we came up with previously. So let's write down our condition that we want to keep the phase, the argument to our cosine constant. So the argument to our cosine was originally omega t minus kz plus phi plus, and we want to keep this equal to a constant. And at this point, we might as well just get rid of the phi plus, because we could subtract both sides, subtract phi plus from both sides, and the right-hand side would still be a constant, just a different one. So we want to keep the difference between omega t and kz constant. If we take differentials of this equation, omega is a constant, so omega dt minus k dz, and the differential of a constant is 0. If I rearrange this equation, then I can arrive at an expression for dz by dt, which in this case we call something special. We call it the phase velocity, u sub p, because it is associated with a point of constant phase on our sinusoid. And rearranging this equation, we can see that it's equal to omega over k. So this is one expression for phase velocity. But we also know that the wave number k can be expressed as the product of omega and the square root of mu times epsilon. And these omegas cancel, and we get the same expression that we had identified for wave velocity before, which is 1 over the square root of mu and epsilon. So this is the speed at which that point in the previous slide travels. And if we were to evaluate this constant in free space, so we substitute the constitutive parameters of free space in here, we would arrive at the familiar speed of light, which is 3 or approximately 3 times 10 to the 8 meters per second. And recognize that if I use a medium with a higher dielectric constant than that of free space, i.e. a dielectric, that the speed of the wave, the phase velocity of the wave, must necessarily decrease, because if I let epsilon be equal to the product of epsilon naught and epsilon r, our relative permittivity, then in general my phase velocity would be 1 over square root mu naught epsilon r, which is the speed of light in a vacuum divided by the square root of the relative permittivity. So the speed can only go down. And that makes sense because we can't have a situation where we have the phase velocity exceeding the speed of light. Another important parameter that we can identify is something called wavelength. So wavelength is like the spatial period of a wave, and we use a Greek letter lambda for wavelength. And let's just write down that it is the spatial period of the wave. So if we go back to this diagram that, or these plots that we showed previously, since this is a plot versus space, we can immediately recognize the spatial period of this wave. For example, we could choose a point here. Let's say, let's clean up this diagram a bit. Let's choose the maximum at this particular instant in time indicated by the blue curve. Let's choose the maxima, successive maxima on this curve. Well, then those 2 points, which we would normally call like some sort of period, this is a spatial period, right? Because we're plotting versus space here. So this is lambda. So essentially this wavelength represents 2 points in phase that are separated by 2 pi, right? Because we know that the cosine function repeats every 2 pi. So let's write that down mathematically over here. We know that the argument to the cosine from up here is omega, and let's say that we're evaluating this at time t naught, so omega t naught minus kz, and if we want, we can reintroduce this arbitrary constant phi plus. So this is the point on our curve over here. This first point over here is when we evaluate the cosine function at time t naught. In this function here, we didn't include the constant phi plus, but in general it could be included, so I've included it here. So this is at time t naught. And now we want to find where we are here. We've evaluated the point on the left, and now we want to find the argument to the cosine associated with the second maxima on the right. Well, that's one wavelength later, right, in space. So if we go to our expression here, we know that the difference between this phase point on the left and a successive phase point on the right, which occurs at the same time, but at a distance z plus lambda, right, because we've moved one wavelength to the right, plus this arbitrary phase constant here, the difference between these two must be 2 pi, right, because the cosine function repeats every 2 pi. What I've basically written here is that we know that cos of x must be equal to cos of x plus 2 pi, right? We know that the difference between x and x plus 2 pi must be 2 pi, which is what we've written down below, where x essentially now is this omega t, is this expression that we have down below. So this difference must be 2 pi, and many of these terms are obviously going to cancel because we're evaluating at the same time. This constant here, phi plus, doesn't matter, and this kz is going to cancel with this kz here. So what we're going to be left with is an expression that says that k lambda equals 2 pi. And so we can solve for lambda in terms of the wave number as 2 pi over k. You may also remember that we can express k in terms of phase velocity. So this is 2 pi over omega times the square root of mu epsilon. But omega over 2 pi is regular frequency. Instead of, we know that frequency and radiant frequency are related through this relation, omega equals 2 pi f, right? So omega divided by 2 pi is just regular temporal frequency f. So this is 1 over f square root mu epsilon. But 1 over square root mu epsilon is the phase velocity. So this is phase velocity, which we call u sub p, divided by f. And perhaps you've seen this more familiar relation between wavelength and frequency in physics courses. The product of wavelength and frequency is the phase velocity, or if we're in a vacuum, the product of wavelength and frequency is the speed of light. Okay, so now we're going to turn our attention to the magnetic field. So we had previously looked at Maxwell's equations, these source-free equations, way back here on the left, and there was these two curl E equations, curl of E and curl of H, sorry, a curl E equation and a curl H equation. And we had said that it's a bit more work to solve these equations simultaneously because they're coupled, right? We have curl of E dependent on time derivative of H, curl of H dependent on time derivative of E. And we were able to substitute one equation into the other essentially to arrive at these homogeneous wave equations that we did on this slide, which allowed us to solve separately for E and separately for H. But bear in mind that E and H need to be related because they need to satisfy these original relations on the left. So while it seems like we could take the wave equation for E and solve for E from that, and then take the wave equation for H and solve for H from that, ultimately the E and H still have to be related with each other, and that is our goal now, is to find how E and H are related. So we had this Helmholtz wave equation which involved wave number, which we wrote down here, and at the bottom of the slide you can see the Helmholtz wave equations for E and H. Again, we could solve for E and H separately by solving these homogeneous differential equations on their own, but in the end E tilde and H tilde have to be related to each other. We don't have unlimited freedom to be able to set them independently. So that's our goal now, is to try to find the relation between the electric and the magnetic field. And we're going to do that for the particular case that we considered here, where we assume that there was only one component of the electric field, which is the x component. So we said that EY and EZ were 0. And we also assume that the solution doesn't vary in the x or the y direction. So we had a uniform plane wave in a plane that's normal to the z-axis. So we're still going to be using this solution that we had here. And in particular, we're going to focus on just one of these two waves, right? Because remember, one wave travels in the plus z direction, one wave travels in the minus z direction. So let's analyze the wave traveling in the plus z direction. Returning to Maxwell's equations in the source-free region, we can now take our solution for the wave that's traveling in the plus z direction and use that in this relation to try to find the magnetic field H. So to do that, we need to evaluate the curl of E, and more specifically, we can find H tilde by taking 1 over j omega mu negative times the curl of E. So let's evaluate the curl of E by expanding that in our usual determinant form in Cartesian coordinates. So we'll put our unit vectors on the top as usual, our derivatives on the middle row, and our field components of the electric field phasor on the last row. Now we're quite lucky in evaluating this curl because many terms in the determinant are 0 here. So we know, for example, in this particular case of the solution, that we've assumed that there are no y or z components of the electric field, and Ex also doesn't vary in the x or the y direction. So in fact, the only component of the curl that will exist in this case is the y component, because it's the only subdeterminant that is non-zero. So when we evaluate that determinant, we have the y component and the partial derivative of EX, but actually it's an ordinary derivative now because there's no variation in the other direction. So ordinary derivative of EX phasor with respect to Z. And also we need to multiply this by minus 1 over j omega mu, which is what we had outside of the curl operation before. So we have a solution for EX tilde for a wave that's traveling in the positive Z direction. It was E naught plus times e to the minus j kz. So we can substitute in this equation. And we can see that h is going to have a y component because of the y hat unit vector here. So let's just drop down to a scalar equation, recognizing that there's only going to be a y component of the magnetic field. Let's take the derivative of EX tilde. That's very easy to do because we're just taking the derivative of a complex exponential function, so the minus jk comes down. So we have minus jk, and then we had multiplication by 1 over j omega mu, and then we have E naught plus e to the minus j k z. Now there's a bunch of terms here that are going to cancel. We have a minus j here and a minus j here. So we have a k over omega mu. And this term we recognize as the original EX tilde. Right? By differentiating EX tilde, the j minus jk comes down and we get EX tilde again. So we can further simplify this as k over omega mu EX tilde. We've also defined wave number previously as omega times the square root of mu epsilon. So if we substitute that in, then omegas cancel. And finally, we can write that hy tilde is equal to the square root of epsilon over mu times EX tilde. So we see that the magnetic field component, Hy, and the electric field component, Ex, and these are the only two components of the fields that exist for this particular plane wave solution, are related through a constant, square root epsilon over mu, which is entirely dependent on the material that this wave is traveling in. It's more conventional for us to write the ratio of the electric field to the magnetic field. The reason for that is that this ratio is very akin to the ratio of voltage to current, right? Because we know that voltage is the integral of E and current is the integral of H. And when you have a V over I relation, that is normally called an impedance, right? V over I is impedance. So we would expect the ratio of E to H to also be some type of impedance. In fact, dimensionally it works out, right? Because the dimensions of electric field are volts per meter, and the dimensions of magnetic field are amperes per meter. So the per meters cancel out, and we have volts over amperes, which is ohms. So this quantity, whatever we call it, is also going to be measured in ohms. So if we look at the relation up above, and just rearrange the relation there, the ratio of the electric field component to the magnetic field component is the square root of mu over epsilon, the reciprocal of what we had above. And this ratio is called eta, which is called the intrinsic impedance of the medium. Again, we see it's only related to the properties of the medium because it only depends on the mu and the epsilon, which are entirely medium parameters. In fact, we can evaluate eta naught, which is the value that results when we plug in the constitutive parameters of free space into this equation. And you'll find that this results in the value of 377 ohms, which is often written as 120 pi ohms, which gives the same answer. So this constant, this intrinsic impedance of the medium, is very helpful because it tells us that the it gives us this constraint between the electric field and the magnetic field that I alluded to earlier. We said that we can't just arbitrarily choose the magnetic field independently of the magnetic field of the electric field. It has to be related. And here we see that in fact they are related through a ratio. In this particular wave solution that we have examined here, where there was only an x component of E, we find that for the magnetic field there's only a component of H that's in the y direction. And then if we take the ratio of E to H, that ratio is this parameter eta, the intrinsic impedance of the medium. So, for example, if I knew my electric field in free space had a value of 1 volt per meter, then I'd know, and this wave was traveling in a certain direction, then I know the magnetic field has to have a value of 1 over 377. At least that would be the magnitude of H. And the direction of H is different from that of E. We notice that in this, after completing this curl operation, returning to what we have above, even though we started with an x component of E, we ultimately arrived at a y component of H, and that's because of the curl operation. And that's a very important observation. We have an x component of E, a y component of H, and variation of both fields in the z direction. Remember, we don't have any variation in the x or the y direction. So this is a very special kind of wave because all three of these terms here are orthogonal. Ex and Hy are obviously orthogonal because x and y are orthogonal. But then the direction of variation of Ex and Hy, which is the direction that the wave is propagating, the z direction, is also orthogonal to the electric field and the magnetic field. So this results in a very special class of wave, which is called a transverse electromagnetic wave, or sometimes this is abbreviated as a TEM wave. And it has this property that the electric field is perpendicular to the magnetic field, and the electric field is also perpendicular to the direction of propagation. So here the direction of propagation is the plus z direction, and we notice that the electric field is indeed perpendicular to both E and H. Simultaneously, H is also perpendicular to the direction of propagation. So all three of these terms, the electric field, the magnetic field, and the direction of propagation, they're all orthogonal with each other. And so we can arrive at this nice picture here of the electric field, which oscillates only in the x direction, or the electric field vector only oscillates in the x direction as a function of time. The magnetic field, being y polarized, only oscillates in the y direction as a function of time. And this wave, if we could animate it, would travel in the z direction. So again, tracking a point of constant phase on either the electric field waveform or the magnetic field waveform, we would find that this point of constant phase would travel in the plus z direction at the phase velocity, which we've established previously. So this is a transverse electromagnetic wave, and as I said, it's a specific solution where we made a bunch of assumptions about the wave to begin with, and that goes all the way back to when we first said there's only an x component, there's no variation in the x or the y directions, and so on. So now we aim to relax this assumption so that we can describe waves that travel in any direction with any direction for the electric field, like any polarization of the electric field. So to do that, we will define a new, slightly different quantity, which is vector wave number. So the vector wave number appears in the numerator here, and we can use the vector wave number to define a unit vector k hat, and k hat describes the direction of propagation of the wave. So in our previous example, k hat was z hat because the wave was traveling in the plus z direction. Now we're letting the wave travel in an arbitrary direction, and that direction is described by this unit vector k hat. And k hat itself is the ratio of a wave vector, or wave number, vector wave number, which is the boldface k in the numerator here, divided by its length, which is just the k that we knew before. So the vector wave number has potentially x, y, and z components. So we have added these terms here. The x component is k sub x, the y component is k sub y, and the z component is k sub z. The length of the vector wave number must obviously be the same as the scalar wave number that we defined previously. So that's expressed with this relation here, which is the square of the length. The square of the length, which is k squared, must be equal to the sum of kx squared, ky squared, and kz squared. So this is equal to omega squared mu epsilon, right? Because we know that k was previously defined as omega times the square root of mu epsilon. So this is how we define the direction of travel of our plane wave. And then if we define an arbitrary position vector r, as shown here, that has some arbitrary x, y, and z coordinates, then we can in general describe our electric field phasor, E tilde, as E naught, which describes the polarization of E, which we haven't elaborated on yet, times an exponential which contains the dot product of the wave number, vector wave number, and the position vector. So if we expand this, this would be E naught times exp minus j times kx times x plus ky times y plus kz times z, if you evaluate that dot product. So in our previous example, we recognize that E naught was just happened to be some value which we called E naught plus, and it was polarized in the x direction, and only kz was non-zero. It was actually equal to k. These two terms were 0. Okay, so our previous example was a very special case where kz was equal to k and E naught was equal to E naught plus x hat. But in general, now we can relax that. We don't need the electric field to be polarized in the x direction, nor do we need the x component and y component of the vector wave number to be 0. So we can now remove all of these assumptions, and this is how we describe a plane wave in phasor form propagating in a specific direction. Now, you recall in the previous picture here that the electric field, and later we saw the magnetic field, also have to be perpendicular to the direction of propagation. The direction of propagation here is described by k, or k hat. And so that means that there must be some relation, there must be some constraint between E naught and k, because these ultimately need to be perpendicular with each other. And we can actually prove this in the general case. We will make use of this vector identity, which is given at the top of the slide here, which just tells us what happens when we take the divergence of a scalar f multiplied by a vector a. And we'll make use of this equation. The reason that we need this is that if we take a close look at our electric field phasor expression, E tilde is equal to E naught multiplied by e to the minus j k dot r. So in this equation, we recognize that this part is the scalar term f, and this part here is the vector term a. So let's try to write out an expression for the divergence of E. The divergence of E tilde, our phasor expression, and making use of this vector identity that we have up above, is equal to the divergence of, just changing the order here, e to the minus j k dot r multiplied by E naught. Okay, so now we'll apply this vector identity directly to this. So the first term is going to be E naught dotted with the gradient of e to the minus j k dot r. And the second term is going to be e to the minus j k dot r multiplied by the divergence of E naught. Now, from our Maxwell's equations in the source-free region, we know that the divergence of E tilde is identically equal to 0. We proved that when we looked at Maxwell's equations in the source-free region. So this expansion here must also be equal to 0. Now, looking at these terms, this term here is the divergence of E naught. But E naught is just a constant, right? E naught just describes the direction of the electric field for our plane wave. So E naught is a constant. If I take the divergence of a constant, this is 0. So this whole term here goes to 0. And we only have the expression, the first term in this expression that needs to be 0. So let's expand that. Let's expand this expression here. So we have E naught. And now let's dot that with the gradient of e to the minus j k dot r. So let's expand the gradient operator. This is d by dx, x hat, plus d by dy, y hat, plus d by dz, z hat. And then we're taking the gradient of this exponential function, which will also expand, e to the minus j k sub x times x, minus j k sub y, y, minus j k sub z, z. And this has to be equal to 0. Well, this gradient operation is quite easy for us to evaluate, because when we take this exponential function in parentheses on the right and take the derivative or the partial derivative with respect to x, only the minus j k x term comes down, right? So we're going to end up with a minus j k sub x, x hat for the first derivative. Similarly, for the second term, only the minus j k sub y times y term will come down and attach to the unit vector. And same for the k sub z times z term. Then, of course, when we differentiate an exponential, we get the same exponential again. So this is left as e to the minus j k sub x x minus j k sub y y minus j k sub z z. And this must be equal to 0 still. So we can basically divide both sides of the equation by this exponential term because it's non-zero. And this term can be, we can also divide out, we can factor out the minus j, right? So this is going to be equal to E naught dotted with minus j. And then what if we pull out the minus j, what's left? We have our vector wave number, right? Because it's k sub x times x hat plus k sub y times y hat plus k sub z, z hat. And this is equal to 0. And again, we can divide both sides of the equation by minus j. And now we've arrived at the fact that E naught dotted with vector wave number must be 0. This makes perfect sense because we said that plane wave solutions are transverse electromagnetic waves whereby the electric field is polarized in a direction perpendicular to the direction of propagation. Well, anytime I have two vectors whose dot product is 0, that means that they are perpendicular with each other, right? So E naught must therefore be perpendicular to K. And this matches our diagram here, which was obviously a specific case, but we see that now we have proven that the electric field is perpendicular to the direction of propagation, which is the z direction here. So what about the magnetic field? Well, we expect the magnetic field to also be perpendicular to the direction of propagation, so we might as well prove that as well. To make this proof, we're going to need this identity, which is what happens when they take the curl of the product of F and A. We know that we can find the magnetic field from the electric field from the relation that we showed earlier. So we know that curl of E, or E tilde for our phasor expression, is equal to minus j omega mu H tilde. So if we're trying to find the magnetic field H tilde, this is minus 1 over j omega mu times curl of E, or we can bring the j to the top, and this would be j over omega mu times curl of E. Now again, the electric field E tilde is the product of a scalar, which is e to the minus j k dot r, and a vector, which is e naught. And again, I've written it in this reversed order here, so we can make use of the vector identity as shown here. So our goal is to use this vector identity to expand this curl operation on E once we've substituted in the expression above. So let's do that. Let's find H tilde. So this is going to be j over omega mu. And now we will evaluate each term in succession. So we have gradient of f. So f in this case, as it was in the previous slide, f is this scalar term here. And we actually worked out the gradient of f on the previous slide. So we'll just make use of that result here. We found that the result of that was minus j times the vector wave number times e to the minus j k dot r. Then we are going to cross this with our vector e naught. And then for the second term, we're going to take our e to the minus j k dot r term here and multiply it with the curl of e naught. Now again, just like in the previous slide, e naught is a constant. So curl is just a very fancy spatial derivative, and anytime I take the derivative of a constant, that's 0. So this term is 0, and that means we can basically ignore this entire second term. So that leaves us with the first term, which we can now just reorganize a little bit. So let's organize this as e to the minus j k dot r. And let's put our, let's express the vector wave number k as a product of scalar wave number k and the direction associated with it. So k times k hat is the same thing as vector wave number. In the denominator, we have omega mu, and then we have this cross with e naught. Now this expression that we see here, k over omega mu, we recognize this. We previously identified this as 1 over eta naught, or the reciprocal of eta naught. So if we now write our expression for H tilde, it is 1 over, so this term is 1 over eta naught, as I just said. So this is 1 over eta naught times k hat crossed with e naught times e to the minus j k dot r. And again, we recognize this term here as e tilde. So we can find H tilde simply by taking the cross product of k hat and e tilde and dividing by the intrinsic impedance of the medium, which is eta here. So the cross product has the property that the vector resulting from the cross product is automatically perpendicular to the two vectors that you're taking the cross product of. So by construction, by definition, H tilde is perpendicular to both E tilde and K hat. Right? And this is the property that we saw associated with transverse electromagnetic waves here. H is perpendicular to E. H is also perpendicular to the direction of the vector wave number, k hat. Again, just for emphasis, we see that the electric field, or the magnitude of the electric field, is essentially given by knowing the magnitude of the electric field and dividing by eta. So again, the magnitude of the magnetic field is always constrained by the magnitude of the electric field via the intrinsic impedance of the medium that the wave is propagating in. So this is an important property of a transverse electromagnetic wave. We've seen that E, H, and K all are perpendicular to each other. And in fact, we can draw ourselves a little diagram to help us remember this. Let's draw the electric field. Let's say the point vertically in this direction here. And let's draw the magnetic field as pointed to the left here. And we know that the electric and the magnetic field must be perpendicular with each other. We also know that the electric field and the magnetic field and the direction of propagation of the wave, which we indicate with k hat, must also be perpendicular with each other. And you can see that the directions of the vectors that I've drawn here is consistent with the magnetic field equation that we've written up above. The direction of H is found by taking the direction of propagation k hat and crossing that with the direction of E. So if we use our right-hand rule, H points in the direction of K cross E. In general, you can see that E, H, and K form what we call a right-handed triplet, because the direction of these arrows is a right-handed type of coordinate system. So E cross H points in the direction of K as well. So all transverse electromagnetic waves obey this relation, and we can use this diagram to very quickly determine the direction of the various field components. Let's say if we only know one of them, or two of them at a time. Let's say we know E and H, then we know the direction of propagation. If we know E and K, we know the direction of the magnetic field.